All right. So the second topic that I'll be talking about, which is one of the domains in Aqua, is machine learning. And like we've been saying many times, there are several, there are several tutorial notebooks online if you haven't already gone through those. And then I'll just be going in detail through the theory behind those. And then I'll also go through one of the notebooks to give you a flavor of how you do this problem. So the problem that we're trying to solve here is we have some data points that have some labels associated with them. So here there's two different labels and they're just colored differently. And they are distributed in some way. And the idea is that you want to be able to use this set of data with labels that you already have, and then be able to use information about this data set in order to assign a label to a new data point that arrives into your system. So if I have a new data point, it lands here, then probably I should assign the color yellow to that data point. So the way that you do this is you construct what's called a hyperplane. So here, this is the hyperplane. It cuts through these two sets of data in such a way that you've cleanly divided it. And then if I have a new data point that arrives and it lands here, I can say which side of this hyperplane is it on. And depending on the answer to that, I assign the label accordingly. And so you can imagine that this hyperplane here, there's some flexibility in how you draw this. I could have drawn it like this, sort of tilted at an angle, and it would still be cleanly separating these 2 points, but maybe that's not the optimal orientation. So what you want to do is you want to construct this hyperplane in such a way that you actually maximize the distance between these two clusters. So this is called the margin, and you want to maximize this, and that will fix the orientation of this hyperplane. And when you do that, when you maximize this margin here, you'll find that there's a few data points that will lie on the boundaries of this margin, and those data points are special data points that are called support vectors. And these support vectors, you can then just use these data points in order to assign labels to new data that you have. So rather than having to use the full, what's called training set, you can just use only the support vectors and assign labels. So this example is really simple because the data is already linearly separable, but usually that's not the case. So here's another very simple example to demonstrate the idea. Here you can't draw a straight line to separate these 2 points. You'd have to draw something that looked like that. So to get around that problem, what you do is you apply a feature map, or you can apply a feature map to your data. And what that means is you're adding another dimension or many more dimensions to your data points in order to separate them in such a way that you can linearly separate them. So here we just added one extra dimension to make this parabolic, and now you can draw a straight line to separate these data points. Does that make sense? Yay! Okay, so the problem, so to make this more formal, this problem, what we want to do is, like I showed in the previous slide, you have this margin that's separating your data points. So what you want to do is you maximize that quantity. Actually, I'm going to go back one a little bit. So you want to maximize this, and it turns out that if you write down the equation describing your hyperplane, so here this is the norm of this W is the vector describing your hyperplane, it turns out that maximizing the margin is equivalent to minimizing the norm of this vector. So if you minimize the norm of the vector subject to some constraints, and those constraints are that your data points must lie outside of this margin, then you can rewrite that simple optimization problem in its dual form, which looks like this. And so let me explain what this is. So these alphas are weights that this is what you're trying to solve for. And these weights will tell you which of your training data points are the support vectors. So any of these alphas that turn out to be non-zero will have a corresponding support vector associated with it. And then the K's here are just the labels of your data set. And then something appears here which is called the kernel matrix. And the kernel matrix is just a matrix where all of the entries are just dot products of your data, but in the feature mapped space. And so this is called the kernel trick, basically, is that rather than having to explicitly specify your nonlinear transformation or feature map to map your data to a higher dimensional space, rather than actually having to compute that function, you can do the kernel trick, which is I'm going to say, I'm going to pick some function to represent my kernel, and then based off of that functional form that I picked, I can compute the matrix elements of the corresponding kernel matrix, and that implicitly represents my feature map. So you solve this optimization problem, and you get some hopefully small number of these weights alpha that are non-zero, and that'll tell you how many support vectors you have in your training set. And once you have those support vectors, you can build a decision function, which is this quantity, where you're summing over only the support vectors from your training set, and then any new data points that you want to classify. And just note here also that the kernel matrix appears a second time. So you compute a kernel matrix in the training phase when you're trying to find the support vectors, and then in the second stage when you want to now classify new data, you have to build another kernel matrix between your test data points and your support vectors. So all of this is well-known classical technique, and so you may wonder, where does the quantum computing part of this come in? And the answer, or one answer, is through this kernel matrix. So what we can do using qubits is you can actually explicitly perform a quantum feature map with your classical data by encoding it onto an exponentially large quantum state space. So you take your classical vector x, and then you apply some unitary gate made of many subset of smaller gates that somehow encodes your classical vector, and apply that to an initial state. So this represents the quantum feature map. So one way of constructing this quantum feature map is with a circuit like this. And this is based off of this paper last year by our fellow IBM colleagues. And what this circuit is it's two layers of Hadamards interleaved with entangling gates. And these entangling gates is where your classical data is encoded. And specifically for this setup, the way that's done is through a matrix of this form. So you have these Z's represent poly Z gates, and then you have some function phi here that you can pick that. It's some function that encodes the entries of your vector. So you could pick like sine of x or something, whatever you want. This tells you how you're encoding your vectors. You multiply with these polystrings, and then you build up this entangling gate, and this is how you're encoding your data. It turns out that so if you want to do this with a quantum computer, you probably would want to pick a feature map here that is not too trivial, because if it's trivial, say it's a separable feature map, which means there's no entanglement, you just have a bunch of single qubit rotations, then you probably wouldn't want to do this on a quantum computer because that's easy to simulate classically. So what you want to do instead is you want to try to find a circuit such as this one that you have confidence is hard to simulate classically, so that you may be able to get an advantage over a conventional technique for solving this problem. And it turns out that this particular circuit family is related to another circuit family which is conjectured to be hard to simulate classically. So if that turns out to be the case, if it really is true that this circuit family is hard to simulate classically, then this provides a starting point for maybe we can get better classification results with this feature map than with some classical kernel. Any questions? Okay, so there's two ways that I want to describe to you of how you can solve this problem with a quantum computer. The first one is called quantum kernel estimator. And basically what that means is you build a quantum circuit that's used to calculate all of the entries of your kernel matrix. So you build a circuit, you execute that circuit, and that will give you an estimate of one entry of the kernel matrix. And you do that for all of the entries. And then once you have that matrix, you can solve the rest of the problem classically, like you normally would. And so how do you do that? Well, the key to knowing how to do that is to look at what is the definition of the kernel matrix. So it's, like I was saying, it's just a dot product of vectors in a feature map space. So if you write that in terms of quantum states, you have this phi represents the data that I mapped onto the set of quantum states, and then this is the inner product with another data point, xi, with the same feature map. And if you just rewrite this in terms of the actual circuit that implemented that feature map, then what you see is you just apply this circuit and its inverse with two different data points, and then measure. And if I get all zeros on the output, the probability of that happening will be an estimate of this one kernel matrix. So here in circuit form is what I just said. So you encode your first data point with a feature map. You encode the second data point, the inverse circuit, the second data point, I measure, and the probability I get all zeros there is my estimate of that one matrix element. And I repeat this for order n squared number of matrix elements. Another way that you can do this is by actually building a quantum circuit that acts as the classifier itself. And this is in the same vein as what we do with chemistry and with the variational quantum eigensolver. So we build a quantum circuit that has free parameters in it that we want to tune such that we minimize some cost function, which in this case is training error. In the case of chemistry, the cost function is the total energy. But the idea is very much the same. So this is called the quantum variational classifier. It starts in the same way as the other method. You still use a quantum feature map to map your data point X, and then you follow that by a variational circuit. And the variational circuit is constructed to have these free parameters that you then use a classical optimizer to update. So what you would do is you run this circuit for a data point, you measure. Depending on that output, you can use a Boolean function to map that to one of your labels. And then you can build up a cost function, which is the training error, and use a classical optimizer to then tweak these parameters theta, and then run this again until you've reached some sort of stopping condition. So this circuit is actually directly representing your classifier. And when you have a new data point that arrives that you don't know the label to, you run it through this circuit with your optimal parameters, and then you get an estimate of what the label should be. Does that make sense? So these two ideas were implemented on the hardware in this paper that I've been referencing. And so they tried these two methods and compared how they did. And the data set that they used was a synthetically generated data set where the data came from the actual quantum feature map that we're using here. So it's a proof of principle that this method could be useful. So the data, this is one example of the data set. The entries are mapped between 0 and 2 pi. And then what we want to do is we want to use this as the training set and then build our classifiers. So here's some results from using these two methods. So this is the accuracy of your classifier. And then this right here represents how deep your variational circuit is. So the variational circuit that you use for this method, so this is what the depth of this circuit here, you can set this circuit up. You have a lot of freedom in how you want to set that up, and you can have layers of entangling gates with single qubit gates, and you can repeat that many times, and that's what this depth represents. So the more depth you have in that circuit, the more free parameters you have to optimize over, and also you probably have more entanglement in that circuit as well. So these data points just represent different experiments that were run and the resulting accuracy as a function of the depth. And you can see that as the depth of the variational circuit goes up, the accuracy of the classifier improves. And then the dashed lines here are the kernel method, which doesn't have a variational circuit in it, so it's just a horizontal line. Okay, so I think Richard said these things as well, but I'll just reiterate a couple of nifty features in Aqua for running these things. So both of these methods are available for you to try out. There's Jupyter notebooks for them. There's been some extensions of it, so you can now, what I explained here was just binary classification, so you have two labels for your data set. You can now do this with more than two labels, and you can also, this has been set up so that you can configure the feature map to be something that you're interested in. So rather than using the exact feature map from this paper, you can tweak this circuit family to something that you're interested in. You can change how deep the circuit is. You can change what qubits are entangled with what other qubits, etc. Okay, any questions before I go to the notebook?
Could you go back to the quantum variational estimator? Yes, the W, I'm sorry, yeah, the W circuit, can we obtain the W circuit quantum quantum mechanically. I mean, because we need some of the parameter to build the quantum circuit.
Yes.
So can we solve the dual problem you showed to us quantum mechanically? I mean, by using the quantum
so
computer.
that's what this method is in effect doing. So in the first method, what I explained was you are just using the quantum computer to build up the kernel matrix. And then once you have that matrix, you plug it into this dual form and solve it classically. This method, it's a hybrid. It's very analogous to what we do with the variational quantum eigensolver with chemistry. So this circuit represents the classifier, and these thetas are optimized to give us the lowest training error. And there's a lot of freedom with how you want to build this variational circuit. Okay, and then I was just going to show you one of the Jupyter notebooks that we have for this problem. So this notebook is just for the kernel method, where we compute the kernel matrix. So the first thing that you do is you want to set up your training and test sets. This particular example is for this synthetic data that I was explaining earlier. So it's called ad hoc data here in Aqua. And you can configure how big of a training set you want, how big of a test set, and then the dimensionality of your problem. So the dimensionality is the number of features that you have, and the number of features is in one-to-one correspondence with the number of qubits that you need. So for the two-dimensional case here, we have 2 features, so we need 2 qubits. And this interesting looking thing here represents basically our decision function that we're trying to learn. And from this map, you pull out some of those data points to create your training set and testing set. So this is just a way of visualizing where the different classes are clustered. The different colors represent different classes. And there's, in this particular data set, there's a parameter called the gap, which tells you how far apart the 2 classes are. So you can tune that. You can make the gap really small and make it harder to classify. Okay, so once you have your data set set up, then you can run the problem. So first what you do is so just ignore this part for now. This is a second way that you can solve this problem. But the first thing you do is you construct your feature map. So here we're using what's called in Aqua the second order expansion, which is actually what is done in the paper. And you can specify the depth of that circuit. Here it's 2 and various other parameters. And then once you've constructed the feature map, then you run this problem. Here we're using a chasm simulator. You can use a state vector if you'd like. And then you just call quantum.run. And so what that run function is doing is it's applying the feature map to your data points, computing these dot products or inner products, building up the kernel matrix, and then plugging it into this dual program and solving it classically. And then what it spits out is various things that you might be interested in, like the support vectors, their associated weights, the kernel matrix you can print out, and then what run is also doing is it's then taking a test set and assigning labels, predicting what the labels will be for that test set, and then you can calculate the corresponding accuracy of that classifier. So that's what's shown down here. Is for this particular data set, we had 100% classification accuracy. And And then this is the array of actual labels of your test set, and then what it was predicted to be. So if you are interested in using this for some other data set that you like, you can just reconfigure this beginning portion, load in a data set that you want to use, and then Aqua will take care of the rest, essentially. Okay. That's all I had for this section. Any questions before the next one? All right.
Besides this, the picture for the artificial intelligence application how can it apply to the other AI application?
I'm not completely sure I understand your question, but are you asking, do we have other AI applications?
Yeah. Besides the classification, is there any other
So
application?
right now, you can correct me if I'm wrong, I think this is this classification problem is what we currently have in Aqua available for people. Yeah. So there's both the variational method and this kernel method, and then you can extend it to multi-class problems if you want. But right now, this particular problem is what we have in Aqua.
But do you know, is there anyone or any publication has something to do, not in your Aqua, but other people would have done something on AI in other application?
Yeah, outside of IBM.
Yeah.
So in this classification problem, or just like generally? Yeah, there's a rather large body of literature. Yeah.
I know some people use the CUA machine. They have some application, but is there any other example or publication they have used the QSKIT using in AI application?
It's possible. Off the top of my head, don't know of any. It would be great if there were.
Well, I mean, you guys are going to release the broader recommendation system stuff, get a huge focus with NIU. There'll be more than that.
Yeah. Baby steps. That's what Katie said. Okay, so the third and final topic is quantum chemistry. So what we are interested in with chemistry is essentially solving a problem of interacting fermions. And so, for example, you could write down the Hamiltonian describing the electronic degrees of freedom in a molecule. And what you want to do is you basically want to solve this eigenvalue eigenvector problem, where the smallest eigenvalue represents the ground state of this particular system. And in addition to that, you want to know, if I can estimate this ground state energy, for example, how accurately can I estimate it? And is this an interesting problem to do on our near-term devices? Can we actually do this? And how accurate would the results be? And would you get anything meaningful? And so what the quantum computer does in this particular case is you take this Hamiltonian that's describing interacting fermions, and you map it onto qubits. And then once you mapped it onto qubits, then you can encode this on a quantum computer, and you can actually make estimates of things like the ground state energy or excited state energies, which is important because in applications, you'd want to know what is the lowest energy configuration of a molecule, what are different reaction pathways, etc. So these things are of widespread interest, and we'd like to know, can we get something meaningful with a quantum computer in this area? So with the near-term devices that we have, this is kind of what I was describing for the classification problem. We have this hybrid quantum classical approach where we use a quantum computer and a classical computer in partnership in order to solve a particular problem. So in this case, we may want to know what is the minimum energy of a system, and the way that we can do that is you essentially parameterize your quantum state, which is analogous to this variational circuit that I was describing in the last talk. And then with this parameterization, you can say, I want to estimate the energy of this system, so the expectation value of the Hamiltonian, for a certain set of parameters. But then I want to pick those parameters in such a way that I minimize the energy. And so the classical computer is used to perform the updates to these free parameters, and then the quantum computer is used to represent the actual wave function. And the advantage of this is that because we're using these two calculation methods in partnership with each other, we can actually use shorter depth circuits than if we just tried to run this entirely with a quantum algorithm. Also, this is interesting for chemistry because we can encode these very complex wave functions onto qubits in a more efficient way than what we could do classically. So if you have a system of n electrons, the state space is 2 to the n, so it grows exponentially in the number of particles that you have. So the hybrid approach which you've already heard many times, is called the variational quantum eigensolver. And the way that the kind of workflow that's used is you start with some fermionic problem, you map it with some transformation into qubits, and then you can describe your Hamiltonian as a string of Pauli operators. And once you've done that, then you can prepare what's called a trial state that represents a starting guess for what your wave function is according to some set of parameters, theta. And then you can use this, once you prepare this trial state on the quantum computer, then you can make measurements at the end in certain bases, add up all of the contributions, and that will give you an estimate of the energy. And then based off of that estimate of the energy, you use a classical optimizer to adjust the parameters. And you repeat this many times until some stopping condition is reached. So the first step is transforming your Hamiltonian, which you can write in second quantization with these creation and annihilation operators that create or destroy fermionic modes, so A, dagger, and A. And you can transform those operators into spin operators or these Pauli matrices and represent your Hamiltonian in this way. And once you've done that, you know how to do that on a quantum computer because we know how to implement these Pauli matrices. So there's various mappings that you can use to do this. Probably the most well-known is Jordan Bigner, but there are others that you can use as well. Let me go back. The idea, though, is that you want to use a transformation that preserves the fermionic anti-commutation relations. Otherwise, that transformation is not a good choice. Okay, so once you've mapped your problem onto qubits, the next step is you want to construct a trial state. And this is a initial guess for for example, ground state wave function of your system. And this is a circuit representation of one way that you could construct this trial state. And this is a particular trial state that is called hardware efficient, meaning that it's amenable to our near-term devices because we can represent these with relatively short depth circuits where the number of parameters grows linearly in the number of orbitals in our system. So this particular trial state, there's layers of these. These are just single qubit rotations where the angle that you rotate by are the parameters that you're trying to optimize. And then you interleave them with these entangling gates. And then you can repeat this circuit many times for some depth. And then at the end, you make these measurements in different bases in order to make estimates of the different terms in your Hamiltonian. So in 2017, folks at IBM, they made it to the cover of Nature for some experimental implementations of some small molecules run on the hardware. So this is a schematic from the paper showing this hardware efficient trial state, what it looks like from what these actual pulses might look like, which with Open Pulse now you can configure that. And then the orbitals that this is for beryllium dihydride that can be represented with 6 qubits. So these 3 plots show for 3 different small molecules. So here, hydrogen molecule, lithium hydride, and beryllium hydride. And these are called dissociation curves. So basically, this is the lowest energy value for a particular internuclear separation. And the idea with this is that if you push these 2 atoms very close together, then there's Coulomb repulsion that makes the energy rise very rapidly. So that's why you see this sharp peak here. And then as the separation increases, you find some sweet spot here where this is the global minimum for this particular molecule. So the dots here represent the outcome for the experimental results. And these don't look super great. They're pretty far off from what we would hope they'd be, and there's some reasons for that. One is the depth of these trial states that we could prepare on the hardware was limited. So if we could have prepared higher depth trial states and get within our noise tolerance, then the outcome of these experiments would be better. And so what you can do to improve these before we have fully fault-tolerant quantum computers is you can use a classical error mitigation technique. So here on the left was the previous, one of the plots from the previous slide where this lithium hydride, the energy that you get from the quantum computer was not very good. But if you use an error mitigation technique where you can actually scale the pulses that you use to implement these gates, that's equivalent to scaling the noise. And so if you run this experiment for many instances of noise, then you can extrapolate back to an ideal zero noise limit. And that corresponds to these dots down here, which is much closer to what we would want. Okay, so there's Richard already went over this. You can pip install the chemistry packages in Aqua, and you can run these experiments yourself if you'd like for different molecules. And there are many Jupyter notebooks going through how to do this. Here's one example of this is some code that you would need in order to compute this entire dissociation profile. This is for lithium hydride. So essentially, you can configure this Python dictionary to specify what kind of qubit mapping that I want to use, what variational form, which is the trial wave function, what do I want to use for that, the molecule, what is the interatomic separation here, and then you can run this for varying degrees of separation and then plot out this entire curve. Here are some of the notebooks that we have that can go through this in a lot more detail. So I encourage you to look through those if you haven't already. Okay, that is, before I go through one of the notebooks quickly, are there any questions?
So I noticed that the very important part is the classical optimization. So I'm wondering if is there any literature that use Qiskit but doing a diabatic quantum computing?
That uses Qiskit?
Even for very simple toy model.
Unless someone else knows, I don't know. One, did you have one? Okay.
So my question is that for the variational quantum eigensolver, can you give some comments on what types of measurements and how many measurements you need to compute the energy of the trial wave function?
So the number. Okay, let me take a step back. So you have your Hamiltonian in second quantized form. You make a mapping from those operators to qubit operators. And that means that you can now represent your Hamiltonian as a string of Pauli operators. The number of terms in that sum and how long those strings are depends on the transformation that you used and if there's any symmetries that you can use to reduce the number of qubits. So that will determine how many measurements you have to make.
How many measurements you need in order to get some sort of some kind of accuracy?
Oh, so you're asking like how many shots do you have to make? I mean, it depends on what kind of accuracy you want. I think the accuracy maybe goes as 1 over the square root of the number of shots, something like that. So.
Thanks.
Okay, so I'm just going to quickly go through one of the notebooks that's online for computing the dissociation profile. There's a lot of intro material that you might be interested in, kind of going into the theory behind it. And then, so here, this is kind of similar to what I showed on one of the slides. You can configure a Python dictionary that represents the molecule that you want to estimate the ground state energy of. So this one is for H2 molecule. And what you can do is you can run this for, so this is using the exact eigensolver, so this is not a quantum algorithm, but it gives you kind of a reference for what a classical result might be. So if you run this, this is the output that you would see, and the ground state energy for a given method, in this case the exact eigensolver. You can also compute the dipole moment for this molecule. And then if you want to do this with a quantum approach, so here we're using two different ones. We're going to compare to see how they do, exact eigensolver and then this variational quantum eigensolver. So setting up the same Python dictionary, you run this problem for different separations of the atoms and then map out the dissociation profile and compare how these two methods do. So you can go through this code on your own. I'm not going to go through it unless someone has specific questions, but and then at the end you can print out this is what you would get. There's two lines here, but it's a little bit hard to see. But it just compares these two different approaches.
Okay, may I ask why this sort of bump? Yeah.
This, I'm not a chemist, so it may be from the particular variational form that was used here. Maybe the depth is not high enough.
Okay.
I don't know. There could be.
Can you show me where is the quantum? Yeah.
So like where the actual VQE is going on under the hood? Yeah, it's very much under the hood. So you run, where is it? It's basically encapsulated in this solver.run. So when you call that, it's performing this classical quantum optimization. Sorry, what? Oh, are you asking where did I select the algorithm? Yeah, it's encapsulated here.
I just made a comment for the curve because this is doing the quantum simulation, so you will have the sampling noise. You will have a sampling noise. Yeah. I think that curve is not perfect match because the shot we use only like 1K. Like we get a step, we run our circuit and then we do the measurement, right? The measurement is a random, it's a sampling. So the sampling, if you do not do enough like a shot, then your statistics may not fit your distribution. So they introduce some noises.
Yeah, so that's the previous question. How many shots do you need to get the more smooth curve or more accurate? That's the question. You want to do large margin and many times.
Yep.
Is it different? The shot means that we have the same circuit. How many times we need to run? Because after we do a measurement, we only sampling from the quantum state, right? So maybe, for example, for some example, Rudy showed we have just to apply Hadamard. We get ideally statistically we should get a 0.5 distribution. But after you do the measurement, the probability you get maybe is 0.49 and 0.51, right? So I think it's not dependent on how many polygons you have. It's purely just because you do the measurement.
If I would expect, if you want to get the unit half and half distribution.
Yep.
If you do 1,000 times, then you may 0.48 and 0.52.
Yep.
But if you do 100,000 times,
yeah,
any approach to
Yeah.
So that's what I mean.
Oh, okay. I saw you. I mean, the same question, the same answer John answered before is like how many polyton you have, because the other I think is relative. If you have many polyton, that means you need to do more measurements. Then maybe that will also affect the variance of your results. Yeah.
In your previous slides, you said the qubit will save the energy. But how? It will calculate more times than it will calculate less time than classical algorithm, or how?
So the idea is that we can more efficiently encode these wave functions onto qubits. So if we have n molecular orbitals that we want to use to represent this molecule, then we need n qubits. But the state space for that system is 2 to the n, so it's exponential. But we only need n qubits to represent it on an actual quantum device.
So it means it means you equals the 1 qubit and the 1 traditional algorithms bit as the same energy consuming, and so the energy saving will.
I'm not sure I understand what you're asking.
It's not an energy saver. You are talking about like if kind of I have a RAN, if I save 1 bit in the classical register, it does it more? And if I save 1 bit in the 1 qubit, it's a very weird. And then in this case, we can save more energy. What do you mean? What do you refer to energy? You mean like a real power consumption, or I think Jen did not talk about the real power consumption in this perspective, right? Then
maybe you're just trying to say, what are you gaining by using the quantum? Yeah, is that what you're asking? What are you gaining by using the quantum?
Yeah, are you asking about what is the advantage we get by using this VQE, or?
Yes, yes. I saw the studies just mentioned that you can save energy. So
I mean, the idea is that for molecules of sufficiently large size, it becomes very quickly intractable to solve that classically. Whereas we can represent that same wave function on just n number of qubits rather than needing 2 to the n bits.
Thank you.
All right. Good.
All right, that's about today's presentation and lectures. And because some of the IBM team will leave tonight, so they will stick here for another 20 minutes. So students, if you have questions, you can ask them now. Okay, so tomorrow we will start at 9 a.m. again. And then tomorrow, Richard will give us the more demonstration of all the application today. Today, just most of the is on theory side. Tomorrow will be more demonstration. Yeah. Okay, so they will stick here for another 20 minutes. So if you have any question, you can come and ask them. All right. See you tomorrow.